In this video, we're going to talk about estimating a population proportion. So for starters, I just want to briefly recap what we know about confidence intervals. So we create confidence intervals around margins of error to estimate the best that we can using our sample statistics, a population parameter. So if this grayish purple line is our population distribution of all the values of, say, mu right there in the middle, let's say it's normal, this dotted line is an example of what happens with our sampling distribution. So whatever values will mimic that same normal curve if things are going well, but obviously the height of that middle point there can vary from the population. And we also talked about this generic equation. We didn't put too much to it, but we're going to work with it in this video. So to find a confidence interval, we start with some statistic from our sample. So that could be p hat, that could be x bar, and then it's going to be plus or minus some critical value, which if it's normally distributed, it will be closely related to that 68, 95, 99.7 rule. More on that later. And then we multiply that by our standard deviation, right? So if we're doing p hat, that's going to be the standard deviation from p hat. If we're doing x bar, obviously the standard deviation from x bar. So we take the idea of that equation and we call it in fancier terms, one sample z interval for a population proportion, which is represented by this equation here, which is essentially what we just talked about in the last slide, but with variables instead of just words. So what happens when certain conditions are met, which we will talk about down here, a C% confidence interval, so 95%, 99%, for the unknown proportion P of our population is represented by these letters and symbols. So P hat, that is our sample statistic plus or minus some critical value. So we have a Z with a little asterisk. I call it a Z star for, shortening words purposes. That's the critical value for the standard normal curve. We love it when we have normal distribution with that same C% of its area falling to the left or the negative Z direction and the positive direction. So that's essentially what area it covers. And then we multiply it by the standard deviation of this statistic here. So we're using p hat instead of p. So it looks a lot like our standard deviation equation. So what are these three different conditions? First up, has to do with our statistic here, our p hat. So we want our sample proportion to be a good estimate of the population. Duh, why would you not? So we have to make sure that it was randomly sampled. So go back and check what those conditions are. This should be random. Second up is this Z star, this Z critical value. So we don't know our population parameter, or P, which is the whole point of creating a confidence interval and checking margin of error and all this stuff. So what we have to do here is check that the large counts condition is met. And so that has to do with our sample size being large enough so that the distribution of our data is approximately normal. So remember, we've got our n times p, not the same p-value of the proportion. So that's our sample size times the probability of those things happening has to be greater than or equal to 10. And the quantity of n times the opposite of that, so 1 minus p, has to be greater than or equal to 10. Our last condition has to do with the standard deviation of our sampling distribution, and that is going to assume independence, so that knowing one thing does not inform knowing the other thing, which is not something that we commonly have. We normally work with a finite population. We know that it doesn't go on forever. We have some kind of quantity to represent that population. Another way to think about it is that we are choosing things without replacements. We're not putting it back into the population. So it does affect our odds of knowing like the next thing that's going to happen. So we have to make sure that the 10% condition is met. And that is where our sample size n has to be less than 10% of the entire population. And that is actually called a standard error, which is essentially to say that when the standard deviation of a statistic is estimated from data, the result is called the standard error of a statistic. Now you may be thinking, wow, these three conditions, they sound lovely. But what happens when one or more of them are not met? So let's talk about it. First up, we have to have a randomly sampled data, true randomness. So, for example, if you collected data using a voluntary response or convenience sampling method, that ain't so random, is it? So that's going to limit us from making inferences about an entire population. You can draw conclusions about the sample, of course, but it does nothing really good for us in terms of a population. Second, we got this 10%, where our sample size has to be less than 10% of the entire population. So that would mean that you are sampling more than 10% of the population. So that's okay. Sampling from a larger part of a population will mean that our standard deviation is too large. So the confidence intervals get a little wonky. They get wider and will capture more than 95% of the population. So we can't really rely on the numbers that we have. We can get a ballpark estimate, but it's not great. And then last and not least, of course, is our large counts condition. So the capture rate for our confidence level here will be lower than predicted. Because if our large count condition isn't met, that means that our sample distribution is not approximately normal. So that kind of throws a lot of the other things out the window. And we certainly don't want our confidence level to be lower than we even predicted it. That's not good. All right, moment of truth. Let's talk about these critical values. Let's talk about how we calculate them. So, as we just talked about, if large counts condition is met, we can use a normal curve. We love it. We want to make sure that we have a large enough sample so that we get a normal distribution, because we love a good normal distribution. So here we have one. And let's say that I want to capture 95%. I want a 95% confidence interval. So what that really means in terms of this bell curve here is that from this negative z star to this positive z star, those are the values that capture our entire area. So z in this example is going to be our z-score, because our mean right there is 0 when we translate to z-scores. So let's say that I want to find this value and this value. So that is going to be a job for our inv norm. Remember that? Remember? So that's when we try to find these values working backwards given an area. So if we know this whole thing represents 100%, 1 minus 95% gives us 5%, which is distributed on the left and the right here in these little blue sections. What is half of 5? 2.5. And move that decimal place to places to the right, we get 0.025. So when we use inv norm to find our critical value, or z star, in this equation, we would use that area, so half of 5%, 0.025. Our mean 0, because we're using a z-score in this example, and a standard deviation of 1, again, because it's a z-score. And so you find this 1.960, which would be negative 1.960 and a positive 1.960 there. So that's what we multiply our standard deviation by in our equation. Handy. All right, there's been so much information thrown at you about confidence intervals. I want to make sure that we can wrap it up in as nice as a little bow as we can. So there is a traditional 4-step process to constructing a confidence interval. First up, you gotta state. So state the parameter you want to estimate and your confidence level. How confident do you want to be? And do you want to collect to the mean, or, whatever you want? So you got to make a plan next. You want to identify the appropriate inference method and check conditions. So those 3 conditions that we were talking about. Third up, you do. If the conditions are met, you can perform your calculations. Congratulations. Because the last step after you perform your calculations is to conclude. So you interpret your interval in the context of the problem. These are 4 great steps for basically any problem-solving process. All right, and let's put those 4 steps to work all together in an example about distracted walking. So the problem says a recent poll of 738 randomly selected cell phone users found that 170 of them admitted to walking into something or someone while talking on their cell phone. So let us construct and interpret a 95% confidence interval for the proportion of all cell phone users who would admit to walking into something or someone while talking on their cell phone. First step in our 4-step process is to state the parameter we want to estimate and our confidence level. So in this scenario, we want a 95% confidence interval for our p-value, which is going to be the true proportion of all of those cell phone users who would admit to walking into something or someone while talking on their cell phone. So our next big step here is to plan, and that is to first identify the appropriate inference method, and we are going to do a one sample z interval for p, which is what we've been talking about the whole video, and let's check our 3 conditions. So first up, was it randomly sampled? Yes, it was a random sample, because it says so, and also I'm sure we have some information about the survey, so yes. And then the 10% condition. Well, I would say that it is very reasonable to assume that 738 cell phone users is less than 10% of all cell phone users. I'll let you Google that if you must. And then finally, large counts. Is it enough to be normally distributed? So we have to calculate our n, so our sample is 738 times the probability of 170 of those 738 participants will succeed or will match our success metrics, and that is greater than 10 by a long shot. And then is the opposite also greater than 10? And that is true because we take our n value, which is still 738, and then we multiply it by the opposite or the complement of that probability. So that's going to be 568 over 738, and that again is much larger than 10. Our third step is to do, which is if the conditions are met, which all 3 are, we can perform our calculations, which means to plug all this stuff in here. Now, we have most of this. We just need to figure out p hat. So p hat is that 170 over 738, because that is what we are working with here. 170 said, yeah, I did walk into something or someone. And so that is going to give us 0.230. We're going to plug that in here, here, and here. So you see that in purple. And then we do need our z star. And we figured that out because we're using the same confidence interval that we talked about before. So that is 1.960. It's close to 2, which if you think about it, that's 2 standard deviations away from the mean in a normal distribution. So that tracks. And then our n is 738, of course. And so we compile all that together and we get 0.230 plus or minus this 0.03 value. And so that gives us a range of 0.2 to 0.260. So about 20% to 26%. Pretty cool. I think I'm kind of ruining the 4th step, so better get to it. So our last step here is to conclude, which is to interpret our interval in the context of the problem. So we are 95% confident that the interval from 0.2 to 0.26 or 20% to 26% captures p, or the true proportion of all cell phone users who admit to walking into something or someone while they were talking on their cell phone. All that being said, did you know that you can construct a confidence interval for a population proportion on your calculator? Yep, you can. So first up, you hit stat, and then you choose tests, and then you go down to 1 prop z int, which is essentially what we have been doing. And then when that screen appears, if you have a more updated operating system, you're going to have things to enter into. Sorry, I'm not sure what it looks like for older operating systems, but if you want to show me your calculator in class, we can make it work. So when that appears, if we want to use the problem that we just worked through, so x is going to be 170 because that is the number of successes, not the proportion of successes. And so n is 738. Our confidence level is 0.95, and then we calculate. And so the thing in parentheses is their lower value to the upper value. So it was really close to 0.2 and, 0.26. And our p hat is 0.230. And of course, our n is 738. And look at that. It does it for you. So the one last thing that I do want to talk about is choosing a sample size, especially when you are constructing a survey or a study of your own. So when you want to figure out a sample size of your larger population, you want to make sure that you have a confidence interval in mind. Might I suggest 95%, for a population proportion P with a maximum margin of error ME. So you would solve the following inequality for n or your sample size. So your margin of error is going to be greater than or equal to that critical value, that z star, times that standard deviation of your sampling population there. So where p hat is a guessed value for your sample proportion, and the margin of error will always be less than or equal to ME if you use p hat is equal to 0.5. So 2 thoughts when you are guessing for your p hat value here and here. So you can either use a value based on a preliminary or pilot study, or from a value from similar studies, because, you know, nobody has an original thought anymore. So pretty sure that there is a similar, if not identical, study out there that you might be looking to adopt a p-value from. Or you can always use 0.5, as we stated up here. The margin of error is greatest at that value, so that guess is going to be conservative, because if the study produces a different p-value than 0.5, your actual margin of error will be smaller, which is a good thing. And one last thing to remember is that the margin of error in a confidence interval only accounts for sampling variability. So that means that, you know, there are other sources of error, like people not being truthful, for example. I do want to work through a quick example with you just to show you how you could determine a sample size according to customer satisfaction. So our problem says a company has received complaints about its customer service. The managers intend to hire a consultant to carry out a survey of customers. So before contacting that consultant, the company president wants some ideas of the sample size that they'll be required to pay for. One value of interest is the proportion P of customers who are satisfied with the company's customer service. So the company president decides that they want to estimate to be within 3 percentage points at a 95% confidence level. So how large of a sample is necessary? All right, so the first thing is I'm going to take that equation that we just looked at, and our margin of error is given to us, 0.03. And it's got to be greater than or equal to that z value. Now we are still using a 95% confidence level, so that inv norm gives us 1.96. And we don't have a p hat value, so I'm just going to go with 0.5. So 0.5 goes in for that p hat and that p hat. And so, of course, we're looking for n. So let's do some algebra and figure this thing out. All right, I need to get that radical by itself because I need to get that n by itself. So I'm going to divide both sides by 1.96, which moves it over here. I'm not going to simplify it because it is a long decimal and I don't want to lose precision. So my next step is going to be to square both sides, which gets rid of that radical. So this is still the same quantity. I get rid of the radical here. You can simplify 1 minus 0.5 to 0.5. And so what I'm now going to do is I want to get this guy by itself. And one way to do that is to multiply both sides by n. And so we get this guy, because that n will cancel, and we give this side an n. And so we want this by itself, so we're going to divide both sides by this quantity, and that is going to give us an n value. All right, so we get this quantity here, n is greater than or equal to this whole thing. And when you simplify it all down, you get n is greater than or equal to 1067.111 repeating. So round that up because we can't have 1/9 of a person, not legally. So the sample must include at least 1,068 customers. So that's going to do it for this video. Congratulations for making it through. Thanks for watching.